This question looks at mass spectra. The mass and abundance of the different isotopes can be determined from a mass spectra. Let's take a look a bit at how it operates. I'm going to begin by explaining a little bit of its operation. The green bar here represents my isotopic mixture, and it's going into an ionization chamber. In an ionization chamber, it's subject to electrons at high speed, and these electrons can knock an electron out of my atom. So here, for example, I'm going to use sulfur. Sulfur 3416 is hit with my ionizing electron, and it knocks out an electron. Hence, I now have two free electrons, and the sulfur now has developed a +1 charge. I'm going to consider three possible collisions. In the second collision, sulfur that weighs 32 is struck by an electron, and it has one knocked off. And in the next collision, again another sulfur 32 struck with a high-speed electron, but this time accidentally a second electron is knocked off, so it develops a +2 charge. I'm going to represent these three isotopes now by the three green bars that you see in the next diagram. They then enter a deflection chamber. Basically, it's a magnetic field that causes the streams to bend. How much they bend depends inversely on the mass. So as the mass increases, the deflection decreases, and it also varies directly with the charge. So I'm going to show my first case, the sulfur weighing 34 bends a little bit off course. The next stream, because it weighs less, is going to bend more. So it's going to be represented here by the solid green stream. And finally, my third stream, which has two electrons knocked off, it develops a +2 charge. It will deflect twice as much. I'm going to place some numbers here on that screen that they've struck. Those numbers represent what we call the mass over charge ratio, which we obtain by using these two numbers. If I measure the intensity or brightness on the screen, I get some idea of the abundance of each of the isotopes. That's presented here in this diagram. I'd like to mention at this point that the mass charge ratio at 16 I use really for an example to show a +2 charge and is negligible in size, but I just can't draw it small enough, so we're going to ignore it. What I'd like to determine now is what's the relative atomic mass of sulfur. First thing I'm going to do is consider 100 atoms of sulfur. Using the abundance that's available in the diagram, I can determine the total mass of the 100 atoms. 95 of them would weigh 32, and 5 of them would weigh 34, giving me 3,210. To get the average mass then of 1, I divide by 100. So 32.2 would represent what we call the relative atomic mass of sulfur. But relative to what? Well, it's relative to the carbon-12 isotope, the most common isotope of carbon, which is set at a value of 12. Let's try another relative atomic mass question. Naturally occurring lithium comes in two isotopes, one that weighs 6 and one that weighs 7. The relative atomic number on the periodic table is 6.94. Determine the relative abundance of each isotope. So again, I'm going to consider a mass of 100 atoms. Now to determine the total mass of the atoms, I'm going to let Y represent the number that weighs 6. So Y times 6, and Z is going to represent the number that weighs 7. And Z times 7 is going to equal 694. That has two unknowns. In order to be able to solve this, I need a second equation. And that is that X plus Y must total 100. So isolating for Z, I get Z is equaling 100 minus Y. And I'm going to substitute that in the next expression. Expanding and collecting like terms, I get the following. And finally, to isolate for Y, I get 6. So 6% of them weigh 6. The other remaining 94 would weigh 7. I hope you found that useful. Thanks for watching.